to session 6, Scaling Up Renewable Energy Deployment from Grid Integration to Energy Planning. I'm very excited about today. We have a group of fantastic panelists. We're going to have our first panelist set the stage for power system planning. The rest are going to give some really great examples of what they've been doing in country. So as we start to see more and more variable renewable energy come online, connected to centralized power grids, this topic of grid integration is becoming more and more important. And grid integration is going to really require an evolution in the way that power systems are planned. And that's what we're going to hear more about today, is how power system planners are thinking about and modeling out these issues to overcome any perceived technical limits on their system. So as I said, we're going to start by setting the stage. We're going to have Jacqueline Cochran, a senior energy analyst with the National Renewable Energy Lab, come up to talk a little bit just about the tools for a holistic approach around grid integration planning so that we have a better understanding, in-depth overview of what the rest of our speakers will talk about. Welcome, Jacqueline.
Thank you, Jen, and I am excited. Very excited to be on a panel with other speakers who are looking into power system planning with high renewable energy futures. So as Jen noted, I will be helping sort of set the stage and situate all these good country examples within the broader framework of how we plan for power systems with high renewables. So first, let me just introduce a term, grid integration study. This is a very broad term. It covers a lot of different things. But a grid integration study is an analytical framework for evaluating how a power system can be planned and operated with high levels of variable renewables. So I'll go into a little more detail in this session about what this actually can look like in different cases, but some of the outcomes include simulating the operation of the power system under different future scenarios, identifying reliability concerns, determining relative cost of actions to integrate renewables, and then also address policymaker and system operator concerns so the system can work reliably and cost effectively. So let me start with a series of questions, because the questions are what help guide how an actual grid integration study gets designed. And so I'm going to talk about 3 categories of questions. The first, where, when, and what types of generation and transmission would achieve RE targets at least cost. So here we're looking ahead at, okay, we want to have a 50% generation target, or our NDC is X. How can we get there? What kinds of generation and transmission infrastructure do we need, and how do we do that in a cost-optimized fashion? Because we want to be able to look ahead across multiple years and think, what is the least cost way of planning for this? The second set of questions. What is the impact of wind and solar on unit commitment and economic dispatch? So here we're looking at balancing. So we've got in that first question, we've built up our system, or maybe we have scenarios with multiple futures. And in the second question, we then want to look at, well, how does that actually get operated? How does the system balance? Where are the transmission constraints? Where do we see renewable energy curtailment? What kinds of reserves are needed? What are the impacts on carbon emissions, fuel requirements? How can the operation cost be minimized? So this is an operational focus. The first one is more capital cost, also including operation costs, but like least cost total infrastructure planning. And the second one is specifically looking at, once you've got that in, how does the system operate? And then the third set of questions is, how quickly can a power system with high renewable energy respond to a real-time disturbance, like a generator outage or a transmission outage? So for example, what's the magnitude and duration of frequency deviation? So this is no longer an economic study like the first 2 sets of questions. This is really like, is the power system going to be technically capable of maintaining reliability? And so here we're looking at much shorter timescales. So here are the 3 categories kind of summarized in some colored boxes. The first one, the capacity expansion studies. This is the optimized generation transmission planning. The second set is the production cost study. So this is looking at how you operate the power system at least cost. And the third are the power flow studies. All of these I want to emphasize again that one grid integration study will not tackle all of these because each of these endeavors is a big effort. But they do relate to each other. So the grid integration, the optimized approach can help look at different futures that feeds into the scenarios that you're evaluating with the operations. And the operation information, which gives you sort of what's online at any given time and when are the time periods that we're most concerned about, like when there's a lot of wind but not much demand. That can feed into the power flow study. Like this is where we want to zoom in and look at a particular challenging period and see how the system responds. So they all relate and they all feed into policy development. So I'm going to go through 3 examples of some of NREL's. I work for NREL, National Renewable Energy Lab, some of our studies on these topics. I won't go into results, but I just want to show you how they differ. So the first is the Renewable Energy Future Study. This is looking at, to what extent can renewable energies meet the electricity demand in 2050 in the United States. And we looked at targets like 80% renewable energy, 90% renewable energy, generation levels, not capacity, but generation. Where do we see the cost optimal development of the generation and transmission system? There's a lot of inputs in the model on capital costs, technology, innovations. Some of the outputs of the model include retail electricity price. So here we're getting a good sense of the capital-based infrastructure choices. This is a recent study. It's almost being published any day now, which is the Eastern Renewable Generation Integration Study. So this is the production cost model, that middle category. And here we're looking at what is the impact of 30% electricity generation from wind and solar, and how does that impact the Eastern interconnection in the US? So there's a lot going on this slide, so let me kind of walk through it. Bear with me. What we're looking at is the Eastern United States. It's all one synchronous grid. And we're looking at, starting now where it turns yellow, that's around midday on one day of the year. And we're looking at every 5 minutes how the balance of the system changes up until close to midnight. And so we can see, so this is at nighttime, the sun is set. Okay, so now we've restarted. The yellow is solar, the dark blue is wind. See, now you can see sunset coming in, more hydro, more black. That's the coal. So you can use this kind of tool. This is just a visual, but underneath it is the production cost modeling where we're looking at every 5 minutes on the transmission system, what is the least cost way of balancing that system? And then that helps us understand implications for what kinds of reserves we need, what does that mean for coal ramping, where do we see renewable energy curtailment, what are the transmission constraints, and these will help us maybe even go back to the capacity expansion and say, you know what, we're going to need more of flexible generation fleet, or we're going to need another transmission line. But it can also just inform what kinds of policy changes, market design changes might we want to take in order to better anticipate the impact of wind and solar. Okay, the third example I'm going to show you is from our Western Wind and Solar Integration Study, Phase 3. This is where we zoom in on that technical feasibility issue. So when you have a lot of wind and solar in the system, how does the Western interconnection respond in terms of transient stability and frequency response? And so this study is used the outputs of a production cost model, when are the times that we're most concerned about, and then then we looked very carefully at, okay, if there's an outage on the line, how quickly does the system recover when you have wind and solar, which doesn't have that inherent inertial response that the large thermal units have. And then the study was also looking at, okay, so if that's a concern, what if we added active power controls to wind turbines and other generators so that we can help maintain it? Is that effective? And the answer is yes, even though I'm not talking about results. So, across all of these three, the key, the thing that we emphasize most when we're doing our grid integration studies is stakeholder engagement. We call these technical review committees. And these are the industry experts who participate at all phases of the project to help set the stage of what are the questions that we want the study to address, are we modeling the system correctly? Do coal units do that? Do we have the transmission lines correct? They help validate our approach, and then also importantly, they can help communicate the results, because if they've been part of the process the whole way and we've been responding to their feedback, then they can also see the results at the end and help communicate that. Because ultimately the purpose of this is not to sit on a shelf, but to actually inform changes in market design, in system operations, in policy, and we want them to be the ones to kind of take this forward. Okay, so really quickly, tips for your own studies. Clearly define the study questions. What is it that you want to learn? If you're trying to measure reliability, what does that mean? What metrics do you use? At what time scales? Do you have the right tools? Do you have the right data? Where can you get the data? Importantly, is the process transparent? Are you making clear what your methodologies are? And then do you have impartial external experts to review the results? And then my final slide is, if you're also doing this as external assistance, so you're helping another country conduct one of these grid integration studies, I have some additional tips. At this point, it's even more critical to have good stakeholder feedback. You want the study to be led or co-led by the relevant institution in the country. Transparency is critical for, you might not be able to advertise the actual data inputs, but certainly the assumptions and the results. These models are not static. There's a lot of effort that goes into creating these models. And you don't want to just do this one time and then throw away the model or the modeling expertise. So we want, these models are usually good for several years where you can continue to ask questions of it, and then you can revise the models. It's much easier to just revise them rather than do this all again. So in-country capacity building is necessary to keep this an ongoing effective tool for power system planning. Time synchronous data is very difficult. Some of these studies require multiple years of solar and wind resource data. Some require just really high resolution solar and wind resource data for 1 calendar year. This solar is relatively cheap to purchase, but wind is much more difficult. It's much more expensive to purchase or produce. So keep that in mind of what is possible or not. There are tricks to get around it, but that is the study is only as good as the quality of the data input. And then finally, software and data sharing. Software is expensive sometimes, especially if you have to do training. So this needs to be budgeted. And also, data sharing can be very time-consuming to undertake. So with planning, in terms of grid integration studies, make sure there's sufficient time available to have like non-disclosure agreements. And that's it, and I will take questions later. Thank you.
As Jacqueline said, I think we're going to take questions unless there's a major clarifying question. I think that we'll do questions at the end of all the speakers, so please remember what you would like to know. So I think Jacqueline sets the stage really well by talking about the 3 types of modeling and the types of questions that those models can answer. And so now we're really going to hear about the application of a lot of those models to relevant questions. First, we're going to hear from Mohit Joshi from India. So Mohit is someone that we have been working with through a USAID and NREL project. He's the deputy manager at the National Load Dispatch Center at POSICO, the power system operator in India. And he, as I said, is the lead modeler on this study. And he's going to talk about evaluating the Indian power system in high RE scenarios and how they're approaching that question.
Thank you, Jennifer. First of all, good morning to all of you. I am Mohit Joshi, the system operator from India. So the topic of the presentation is how are we evaluating the high RE condition in India. So I'll start with the overview of the Indian power system. It's a 300 gigawatt installed capacity, and the peak demand is around 150 gigawatt in India. We have a current installed capacity of renewable energy, 43 gigawatts. We have most of the transmission is at the 765 kV level or at the 400 kV level. We have around more than a lakh lines in 400 kV. So now we start with the concept of building the grid. You all must have been aware by this time that India has a huge ambition of 175 gigawatt RE generation by 2022. So for that, it is important that we need to simulate what is going to happen in 2022. For that, we are partnering with US to evaluate the impact of high RE in the Indian system. So that is what we call the RE integration studies. So basically, there are a lot of agencies who are involved from the both sides. From India, the policymakers, Ministry of Power, system operator POSOCO, and transmission planners CTU and CA. From US side, Department of Energy, USAID, USEA, NREL, and LBNL. So when we are doing certain kind of studies, there are a lot of answers which we are going to get from that study. But from Indian context, we are finding these answers. First of all, we would like to know what would be the ramping requirement in 2022. What kind of generators do we want? Next, how much RE penetration can we handle successfully without any curtailment? Or if there is any curtailment, what kind of solutions do we need? What are the potential stress area? What would be the line congested in 2022? What would be the optimal hydro operation by regions, including pumped hydros? And last but not the least, what would be the cost of operations in 2022 with high RE scenario? Now, with respect to India, we are studying these 4 scenarios. The first scenario is 50 gigawatt wind and 20 gigawatt solar. So this is kind of a normal scenario which we think we're gonna achieve by 2022. Then is 60 gigawatt wind and 100 gigawatt solar. Then a high wind scenario, 100 gigawatt wind and 60 gigawatt solar. Then high wind and high solar scenario, which is 100 gigawatt wind and 150 gigawatt solar. So the idea behind studying these scenarios is that we do not know which target we're going to achieve in 2022. So it is important that if there is some kind of a deviation, we should know what is the impact of that deviation on the system operation. Next, in any RE integration study, the first and the foremost important thing is the preparation of base case and data collection. So what all data do we require? The first is the power system network. We need to model load generation and the transmission network. The next important thing is constraints. We need to identify what are our constraints, such as ramp rate of generators, minimum generation constraint, water inflow constraint for hydro reservoirs, interface limits between the control areas, outage rate of plants. We all need to model this. Then we also need to have some kind of forecast for 2022, like load forecast, generation capacity expansion forecast, renewable generation forecast. Then some of the commercial parameters we also need to model in, like variable cost of generators, heat rates, and the hurdle rates. So we have modeled all these into our base case scenario. Now, how do we proceed further? The first step is that we have to build a model for present power system and then validate that model for the present operation. So we need to tune up different parameters so that we have a model which reflects the actual operations. Then we move on to the future year model. For that, we need to forecast load and the necessary capacity to meet that load. Then comes the final scenario for 2022, in which we have to simulate power system under different conditions and see the results. Now, when we are doing any kind of RE integration studies, we are doing a lot of assumptions. And those assumptions would not be true at that point of time. So we have to do some kind of sensitivity analysis. What if that value is not that? So we are doing some kind of sensitivity analysis also in our studies. First is the load curve. So whatever load curve we have assumed for 2022, if that is not true, what will happen? What will happen if we do not have that much flexibility reserves? What happens if we change our dispatch from 15 minutes to 5 minutes? What happens if we have more flexible generation in future? So all these questions would be answered if we do some kind of sensitivity analysis. Now I'll show you some of the sample results which we normally get from our RE integration studies. So this shows the ramp rate that I talked about. So on the left side, you'll find the base case, and on the right side, you'll find the high solar scenario. You'll see when there's high solar, the ramp rate requirement of subcritical coal machines would go up. But this is not the actual results from the study. These are just the sample one to show you what should we expect from the studies. Then we should also get how many generators are going to their minimum values when we have high solar. So if you see on the left side, it's the base case. On the right side, it's the high solar case. So we can see that more and more machines, they are going to their minimum values when we have high solar scenario. This is all from my side. Thank you so much.
Thank you, Mohit. 175 gigawatts is very impressive by 2022. Think you're going to make it? That's great. So we are now going to hear for Dr. Werner Siemers. He's an energy system analyst at QTech Institute in Germany. He is a process engineer, and he has worked in the region on biomass as well as many other issues related to renewables grid integration. So welcome. He's going to talk about scenario development for 100% renewable energy future.
Thank you for the nice introduction. You have seen the title. So I'm coming from Germany. Our issue is still to plan on 100% renewable energy future. Let me first introduce very quickly my institute. It's an applied research institute and working on renewable energy and materials. So our vision is, besides being 100% renewable, we also have to be 100% recycling. So besides energy, we have to have a look on the materials. Also, these are fossil resources and they're going to end somewhere. They're going to be too expensive. So both have to go together. We do that on 4 departments and on some 100 employees. I'm working in the energy system analysis department where we do scenarios, we look at the system approach, renewable energy and energy efficiency as well. I myself, I'm quite active in the energy systems, more on the hardware side in Germany, and I have some experience in Southeast Asia on biomass, energy, biofuels, and biogas a little bit. Let me come to the presentation of our study, what has been done, not for Germany as a whole, but for a state in Germany. We have 15 individual states in Germany, and this one state is Lower Saxony, which is in the northwestern part of Germany. And we have been contracted by the ministry to do scenario analysis, leading to substantial reduction of greenhouse gases. And we opted to present 2 different scenarios. The one is 100% renewable energy scenario, and the second one is at least 80% greenhouse gas reduction. I will come to the difference between these 2 scenarios later. We have put the time horizon to 2050, as others do as well. And we want to tune that scenario really to the local conditions. This means what is the political impact, the political actions the state has to do to reach this target in 2050 with 100% renewable, relying on the own resources. So don't talk on imports of energy, for example. And we have to include all energy demands. This is vital in our situation. Power is only a small portion of our energy demand, of our input energy, what we have. So we have to look at the heat demand, we have to look at the transport issues, and we have to look at the materials side, because also materials, plastic bags, they are produced out of oil. So if we don't want to have CO2 in our system, we have to find alternatives to plastic bags and other materials. we had to set some, let's say, framework conditions. We have seen other scenarios here. We used backcasting. So what we actually did, we defined our situation in 2050, what shall it look like in 2050, and then we calculate back in what steps in the different years we have to achieve what intermediate results to reach our final scenario in the year 2050. We define our calculations on the area. So we have to look how much area we have at hand, what do we need for agriculture, where we do have forestry, where we have our buildings and streets and all these other stuff. And then we can decide where to build wind power plants and where to have PV systems installed, because these two, besides biomass, would be the only energy sources that we can tap. And then what we see is that our infrastructure will turn to be an electricity infrastructure. We don't have fuels, we don't have coal. So everything what we do is electricity. Wind, solar, hydropower, and biomass produce electricity. And then we have all this electricity. It can consume directly for power, for heat, for transport, and for the materials. Or we have to store it in underground storage as a hydrogen or as biomethane. Or we have to convert it, as I said, into biomethane or into other liquid or gaseous intermediate storage options. The last framework was the solidarity principle, because Lower Saxony is a large area and renewable energy has to produce on the area, but we have cities nearby, so the cities can install wind parks. So we have to take part of that load as well. They have to supply energy for highly densely populated areas. In turn, we are getting, let's say, material goods out of the cities and maybe financial inputs out of the cities. Leading, let's say, fixtures for our scenario had been an economic growth of 0.7%, but this should go together with a higher energy productivity. We have a decrease in population, minus 12%, which is still valid in Germany, besides the influx of refugees into our country. And what everybody says, before you go to renewable, we have to increase efficiency. So we were looking at all sectors and defining decreased demands. For power in all sectors, we estimated 18% reduction, which is not too much, but we are on a good way. In residential heat, we will turn everything into electric-driven heat pumps. There will be no gas, no oil anymore in our buildings. We will build low-energy buildings. We need a high rate of renovation in our buildings, and everything will be electric. Low energy demand, and then it could be supplied by electricity. This will save 66%. For process heat in industry, we have to increase efficiency and also shift there from fossil fuel to power, if possible. This gives another 24%. In transport, we have to electrify all individual transports. We have to electrify most of the goods transport. Only airplanes, large ships, and long-distance lorries will use liquid fuels, for example. 88% of individual transport will be electric. Only electric cars around. This will give us 53% on energy reduction. So all together, we would reduce from 340 terawatt hours in 2012 to 180 terawatt hours in 2050. And then we find a summary of our reduction. This is a reduction of energy in there, and we have the composition of our production in a 100% scenario. We will see it's wind, photovoltaic, and biomass on the right side, and a little bit of other renewable resources. The The second option was, besides 100%, we look at greenhouse gas reduction scenario. For that, we have to look at the non-energy-based greenhouse gas emissions from agriculture, from waste, from industry processes. If we look at that, we have to get a little bit more than 10% for non-energy. So we have to allow non-energy greenhouse gas reductions. This leaves us a small 10% of still fossil use, which can be seen on the left side on this 80% greenhouse gas thing. So we are able to reduce our solar, our photovoltaic part a little bit. We can reduce our wind part a little bit. But basically, it's the same shift to wind towards photovoltaic. As a result, I said we have area-based calculations. The first one is the solar roof area. In 2012, we have 0.5% of the building and open area, which was our base of that. In both scenarios, we go to 7% of that area. It means 75% of all possible solar area, roof areas is solar area. Solar parks, we start at 0.08. We can keep to that in the 80% scenario, and we have to go to 4.5% of the total agricultural area being turned into solar parks. Wind onshore has to go to 1.4% or 2.1% in the future. Wind offshore, the part we can take for our Saxony, another 1% or 0.5% between the two scenarios, and energy crops would stay more or less on the same area. A last alternative, a last question on cost. So we did calculate the cost in the two scenarios and one business as usual path, and we see it's more or less leveled out. So we have higher levelized cost of generation. We have to put in more cost for additional grid network and for long and short-term storage in our two scenarios. And then we have the fossil generation, which costs, the running costs are higher because they have to pay for the fuel, and the span is higher depending on what CO2 cost we will factor in and what rises of energy prices we are going to assume. So basically, we would say it's not more renewable energy, 100% renewable energy is not more expensive, no longer more expensive than the fossil path. As I see, I'm running 1 minute out of time, but this is my last picture. Of course, it's open for discussion. Many more aspects can be discussed. I haven't touched the storage option. Technology development is there. This is a present technology, what was based on our scenario, but technology might change. We might get more efficiencies somewhere. We can optimize the system. We have to talk on the material demand. We have to talk on these non-energetic greenhouse gases, which are also an issue, I think, in Asian countries. Many more to come. Here's my contact. And the last slide doesn't come up. I don't know why. Yeah, sorry. It's only for thank you for your attention.
All right, thank you. So now we're going to hear about the dreaded four-letter word curtailment. No joke. American humor. We're going to hear from Liutong Zhang, who is a senior manager with the Lantau Group, and he's been working on analysis of energy markets in the ASEAN region, and most recently, he's specifically been looking at curtailment in China, which is becoming an even bigger issue.
Hi, good morning. I'm Liutong from the Lantau Group in Hong Kong. Just now, Dr. Simmers talked about 100% renewables in the entire group. Maybe it's possible, but let's now talk about one of the key challenges that the renewable developer in China face at the moment. Basically, the curtailments for wind and solar are very high in the past few years, and at least for now, we don't really see any possibility that it will improve in the future. So this slide basically provides some context for the curtailment situation in China. And for wind, the current curtailment amount is about 34 terawatt hours in 2015, and solar is about 5 terawatt hours, and for hydro is around 50 terawatt hours. So the combined amount is actually quite material. It's almost equivalent to about 2 times of Singapore's power consumptions. And on the right-hand side, you can see the details about the wind curtailments. And one of the key unique feature of the Chinese power sector is basically the resource-rich regions are actually located very far away from the load centers. So for the curtailments, the curtailment mostly happens in inland provinces like Jilin, Xinjiang, Inner Mongolia, and Gansu, and you can see that the curtailment rate can be as high as 30% in recent years. And so generally for most of the existing renewable developers and any potential new investors, they always the question they always have will this one get better? And for us, the long-term group, we basically use 4 lenses to try to analyze how curtailment will change in the future. And firstly, we look at the market fundamentals, basically the typical supply-demands growth in the futures. And we also, for each provinces, we always try to look at the local level and then look at the more high level, at the regional level, and then look at the nationwide level. And the other important thing is we also have to look at the supply and demand characteristics, basically how the timing profile of the wind generation and how does it match with the demand side. And the second area that we will always look at is, of course, the grid infrastructure, similar to any other power project. And also the third one is the competition and commercial. And the last one, of course, is whether the government has any policies trying to address the curtailment situation in China. And let's just look at the first one, the fundamental. For this one, I look at the supply and demand situation in China from the nationwide level. And at the national level, you can see that actually Chinese power demand started to slow down quite a bit since 2012. But in terms of the supply side, they continue to build new coal plants, new hydro plants, new nuclear plants. Of course, they also built a lot of new wind and solar plants. And if we look at from 2012 to 2015, on average each year, actually the surplus capacity that they build each year is about 90 gigawatts, which is almost the same as the installed capacity in the UK. And that amount over the past 4 or 5 years, it adds up, it leads to a very high reserve margin that you can see in China at the moment. And if you go to China now, everybody is. 5 years ago, people were talking about power shortages in provinces, power shortages in a lot of cities. But for now, you talk to any of the power generators, basically they are talking about the potential large power surplus in China. And it basically affects hydro less, but basically affect coal, wind, and solar. And that is becoming an increasing challenges for both the developers and also the governments trying to address this issue. And for now, it's still like the Chinese power developers still has the habit trying to build and build. It's like even if you look at last year, they just approved coal. They on average basically approved about 2 large coal projects every week, and it's very difficult for at least for the Chinese engineers to shift to a new era of slow demand. How they are going to respond to this slow demand scenario and increasing economics of how they are going to integrate all these new wind and solar into the system. And And if we even look at the local level in the inland provinces, actually the supply and demand picture actually becomes more stark. And for some provinces, the reserve margin is actually more than 100%. That basically saying that if on average every power plant can only run at half of their rated capacity in order to just to serve the demand. And the other, let's just come back to the wind and the renewable powers. And the other key challenges is actually, let's say, look at for our, we did a Jilin wind curtailment study recently, and when we try to look at how the wind generations and the load profile matches, and on a daily timely basis, basically, I think this is more or less expected. Wind speed is the highest during the nighttime, but the load is the lowest during the nighttime, and so wind doesn't really match very well with the load. But more significant, let's look at the monthly basis. Basically, if we look at the winter and springtime, wind speed is generally higher as well. But for the load, it's not as high as during the summertime. And the other key thing is for the coal-fired power plants in the inland provinces, basically most of them they call it combined heat and power, and they basically supply both heat and power to the consumers. And during the winter and springtime, basically they have to supply the heating requirement to the consumer, and heating requirement basically determines the utilization hour of the coal plants, and because of that, it's so the minimal, you can say the minimal utilization rates of the coal plants in China during the winter and springtime is basically, most people say it's about 70% or 60%, but for wind and solar, because of that, they have to curtail wind and solar during the spring and winter times, and there is, at least at the moment, there is no easy way trying to resolve this conundrum, saying that, I mean, the coal plant has to run to supply the heat, but at the same time, they will also generate the power to squeeze out the wind and solar power generations. And similarly, if we look at the hydro curtailment, basically, hydro is very seasonal, and during the wet seasons, they generally quite a high curtailment during the wet season, but during the dry seasons, they're generally quite okay. And the other, if you search the public news, one of the usual thing that you will find is the development of the ultra high voltage transmission lines in China, and that's mainly because they are trying to transmit the power from the resource-rich area in inland province to the load centers, but actually when state grid try to have the government to speed up the approval of these UHV lines, one of the key arguments is that this UHV line is going to be able to transport the curtailed wind and solar from the inland provinces to the coastal areas. But as the picture becomes clearer now, it actually put a very, very big question mark, mainly because for those ultra high voltage lines, they are very, very capital intensive, and it's almost impossible to just operate for 20% on average. So generally they will have to have base load generation to support those lines, and the base load generation is generally in China is basically large coal power plants, and that's why at the moment there is still a lot of new coal-fired power generation that are still planned and are very likely to be built in the inland province, trying to support this UHV lines to transmit power from the coastal area from the inland province to the coastal area, and this actually can add into the overall capacity in China at the moment if the demand growth doesn't pick up, and that can make the curtailment situation even worse potentially. And the other thing is for the UHV line is basically there is a lot of tension between for the coastal area, they have their local generation, so they don't really need more power from the inland provinces, and this tension is increasingly becoming an issue, and it's very, very hard to resolve this because even it's directed by the central government saying that the coastal area has to take more power, but the local government will always try to put their local economic development at the first priority. So we'll see how this pans out, but for now, it seems to be, unless there is some magical bullet that the demand grows, the power demand consumption in China start to grow again. Otherwise, the whole sector will probably have to go through a very few years of quite difficult years in the coming future. And there are different kinds of policies that are proposed by the government to try to address the curtailment issue. And in general, this policy is very nice, but it is very hard to be implemented in China. And to me, the most positive one is probably China, if the local government is really being able to try to slow down new builds in wind and solar and also coal plants in the future, that will probably would be the most positive development. So, I mean, in summary, basically, for now, we see that the renewable curtailment in China will probably get worse in the next few years, and hopefully it will, at some day, will become better after, let's say, 2020 or 2025. For that one, it's hard to say. And the last slide, I just quickly show that is basically our in-house model. We try to, for each province in China, we try to map the hourly, on average hourly, how the power balances try to pan out, and in order to get these balances, what will be the curtailment amount for wind, solar, and hydro, and that I also show one of our illustrative forecasts in Jilin for one of our recent studies. So next one.
So we're going to go from a very large system to a slightly smaller system as we talk about Sri Lanka. So we have a really unique presentation. We're going to have a tag team presentation from Latika Atanayaka. How did I do? Pretty good. And Guyana Alejandra. And they're both with the Ceylon Electricity Board. Latika works on the generation side, and Guyana works on the transmission side. So we're going to hear about both perspectives as they start to bring in more renewables onto this small system.
Thank you, Jennifer. So, as explained, me and my colleague Guyana is from the Ceylon Electricity Board. So, let us explain the study that we have carried out last year to look around how to integrate renewable energy into the Sri Lankan grid. So, brief description about the Sri Lankan system. So, we have around the peak demand around 2,400 megawatts, and the per capita consumption is around 562 units last year, and the demand is growing around 5 to 6%. And we have mainly hydro and thermal owned by Ceylon Electricity Board as well as private thermal plants. So this graph shows the behavior of the thermal and hydro generation in the past 10 years. When considering mini hydro, wind, solar and biomass, which are present in the Sri Lankan system, we call it non-conventional renewable energy. But now we have changed that because these technologies are no longer, we can't call it as non-conventional. So we have changed it. Allow me to use the word NCRE for this presentation. So at present we have around 460 megawatts installed capacity, and this is the methodology that we have used. First, we define scenarios that we are going to analyze. In the middle you can see we had a reference case which has no NCRE additions in the future, and we did intermediate scenarios, and the extreme cases 20% NCRE additions in the future. So in between that, we did several practical scenarios. So usually we do long-term generation expansion plan, transmission studies, and short-term operation dispatch studies separately. But in this study, we combine those studies, and we model the annual profiles of the wind and solar, mini hydro, and biomass plants, and we input it to generation optimization, and that output we use to for 20-year period in the future. So we from that output we did transmission network studies and operational dispatch studies for 10-year period separately. So then we analyzed the off-peak demand, what happened in the extreme conditions, the dispatch, and whether we can accept that results or not. And finally, we analyze the energy and capacity contributions of these wind solar plants, and curtailments, if there are any, and the economic analysis. So we studied 3 seasons in the year: dry season, wet season, and high wind season for the operational dispatch study. And for the variation of the demand, we studied weekdays and weekends separately. So this is the wind modeling. We consider 4 main locations in the country which has good potential. We use continuous 1-year data available at that point for these 4 sites, and the graph shows the monthly average wind speeds. You can see from May to September it's a high wind season. We use the system advisor model of NREL to model the wind output, and likewise we did modeling for solar and mini hydro. We get the past 11 years data from our dispatch studies, and we construct a model for energy and capacity contribution. So the plant factor of mini hydro is around 37.4. For the biomass plants, we model it as thermal power plants for small scale capacity. This is the planning criteria which enforced to us in the grid code, so we adhere to that. And the NCRE additions, this is the final results for the 10-year period. We add NCRE from 11% at present to around 23% in 2025. So the curtailment observations, there are few small curtailments from 2020 to 2024. That is because the operational limitations. So the curtailment in the off-peak, that means in the night, early morning, and in the week ends, there are some curtailments in the daytime also. So these are the percentage, but it's quite low. The maximum curtailment we observe is the 3% from the NCRE generation. So the cost comparison, it's for the 10-year period, the incremental cost is around 140 million USD. So in 2025, we add a pump storage power plant to the system and observe what is the behavior. In the off-peak period, it's pumping, and peak period it's generating. So we analyze that behavior also. So GAN.
Hi, I'm Dan. I'm working in the transfer planning branch, and I'm going to talk about the transfer planning study of this grid integration. So this is the present Sri Lankan transmission network, and you can see the present wind and solar locations. And in the future, there will be 375 megawatts of Mana wind park in the northeastern and in the northern also. This is the transmission network study. So in this, we prepare base cases to analyze the worst conditions, considering the loading and the generation mix. And then the renewable energy plants are allocated to the grids, considering the potential of those renewable energy sources. So then, for this, there are two study scenarios. One is if there is no NCRE in the future, and the other one is with the NCRE. So this is to determine the transmission infrastructure costs needed solely on NCRE addition. So there, first we study the steady-state system analysis, considering load flow, contingency for all the cases, for both scenarios. And for transmission stability, we select the minimum load case where our system is weak. Because in that case, only the base load power plants are there, and the inertia is very low. So if 1 unit of that old power plant trips, whether we need to find whether the system is stable. So this is the 2022 system where we carried the system stability studies, where it shows that the system frequency is stable. And however, this is for the practical case where we studied a business as usual case, and for 20% NCRE case, we observe the frequency is stable, but there is load shedding. Stable the power system. So that shows that for this condition, the system is stable, so there is no problem. With the steady state also, there is no problem. And as a conclusion, during the initial years of operation, the NCR is able to replace the marginal high cost oil power generation. And however, in the end of the study period, NCR generation is restricted with coal power generation. And also we observe some curtailments during that period with the operational restrictions. And also in all the studies, coal plants were kept at minimum load condition to absorb more NCR in that stage. Therefore, we did not get the cost of running coal plants in the minimum load, the efficiency losses, and to this study. And from this study, we recommend in the future coal plants to be designed to deload up to about 35%, and in order to absorb more NCR. And also, all future NCR plant tariffs should reflect the economic cost. However, in 2025, we are introducing pump storage power plant. So with that, the NCR is operation will be smoother, and with the coal plants, it can be operated more economical. And finally, we think that we need to carry this study periodically, because the NCRE's potential may be varied in the social, difficulties, and environmental effects. So we need to periodically study. And also, we have said that for this study, the planned transmission and generation projects needs to be implemented at time. Otherwise, there will be implications.
think that's a great example of how to utilize these studies to not just identify the challenges in the system, but also some of the solutions, and in this case, identifying something like pumped storage to alleviate some of those issues. So we're going to take some questions. There's actually several seats up here for those that are standing and would like to sit down for the next 20 minutes. We're going to take some questions from our panelists from the audience. There are several microphones, so if you can please speak into a microphone and tell us your name, your organization, and then your question.